Picture a world where the hum of electricity permeates every aspect of our lives, from the devices we hold in our hands to the vehicles that transport us across vast distances. This is the world of the electrification of everything, a paradigm shift that promises to reshape our relationship with energy and power. As once analog and unpowered items are augmented with electrical systems, we find ourselves at the precipice of a new era. But with this transformation comes a challenge: the need for power switching and integrated circuits that can keep pace with the extraordinary demands of our increasingly electrified world. From electric cars to heat pumps and data centers, the appetite for power grows ever more insatiable. Novel technologies like silicon carbide offer a glimpse into a future where energy density and power density reach new heights, enabling devices to operate at peak performance for longer periods. Recent news stories highlight the global changes in power demand as nations grapple with the infrastructure required to support this electrified future. Yet, even as we face these challenges, the pace of innovation offers hope. With each passing day, brilliant minds are developing solutions that will propel us forward, harnessing the power of electricity to create a more sustainable, efficient, and connected world. How can Microchip technology help manage the electrification of everything?
Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience.
Our guest today is Clayton Pillion. Clayton is Vice President of Microchip Technology, manages the Silicon Carbide business unit. He joins us today from our global headquarters in Chandler, Arizona. Welcome, Clayton. Thank you for joining us on Beyond the Microchip.
Well, thank you, Dana. Glad to be here.
In the intro, we briefly talked about the electrification of everything and how it's going to dramatically impact our lives in the very near future. Tell us about it.
You know, in today's world, we are seeing such massive transitions from mechanical systems to anything that needs to be driven by electricity and therefore consuming electricity. And you're seeing it everywhere you are. As you walk through your neighborhood, you drive to the office, you go to school, you're seeing the impact of electrification. Over the last decade, we've only increased our demand by about 5%. As we look forward, we're looking at 20-30% growth in electricity needs because at the end of the day, everything we do is converting to electricity. There's more motors, there's more EVs, and there's more devices that consume electricity. And the ability to deliver it to us with the omnidirectional grid, our ability to consume it, and our need, therefore, to be incredibly more efficient in all that we do.
So we're talking about switches over to transportation. We're talking about electric vehicles. We're seeing electric kind of push its way into aviation. Let's talk about eVTOL.
So eVTOL is a new class of aircraft that is electrically powered, and it's designed to kind of blend the helicopter, the airplane, and really to ultimately look like what most consumers would think is a drone. And the idea here is you can take passengers short distances, and you can do so with a relatively clean environment. And to do this, you have to consume a tremendous amount of electricity, far more than what your vehicle would consume. And therefore, you have to have technology that is incredibly efficient. Obviously, you have to be very lightweight in an eVTOL. You can't have a tremendous amount of battery weight. And therefore, everything that you store, you want to convert to power to help you fly. So silicon carbide plays an instrumental role there in driving the motors and converting that electricity from the battery into ultimately you staying in the air when you want to be.
Yeah, the last thing you want is to come down.
Yeah, at least not in an uncontrolled way.
There's going to be electrified planes. We've got electrified trucking. There's obviously an increased amount of electrification in the industrial sector. We're also seeing things that are electrified that were traditionally analog. So you mentioned the last 10 years, 5%, and now you're talking about 20 or 30%. So we're looking at 5-6x of the need. Is that going to be some of the conveniences that were accelerated in COVID, like paper towel dispensers and faucets and touchless sensors? Or are we talking about something much larger?
Wow, I should have done COVID at your house because it sounds fantastic with all those gadgets. Yeah, I mean, definitely you're seeing more and more appliances having electric control, electronics, communications, all that takes power. But you're also seeing things like EVs, right? Electric vehicles. You know, for instance, if the average EV drove the average distance a year, I mean, that's like running another HVAC in a pretty good sized house. For a full year. And, you know, we live in Arizona. It's the desert. We would definitely not be able to maintain all of our HVACs running plus an extra one. So silicon carbide plays a critical role there in really helping drive the efficiency of that energy conversion. So as the omnidirectional grid delivers it into the house, you want to be able to efficiently convert that into the very target you're looking for, whether it's a EV charger or running your paper towel dispenser so that you don't hurt your hands. Other factors like that, you want that absolute conversion. And in today's world, it's very hard to add fossil fuels. It's very difficult to add large scale utility level type power generation. So now the idea of the microgrid in your house,
right?
The ability to have some solar on top of your roof that goes into a battery. You could use it either when you need it or possibly when there's a peak demand. You know, if you think if every house had a reasonably sized battery and some PV cells on their roof, maybe you don't need the next power plant, or maybe you need a smaller power plant. So it takes this classic model that hasn't changed in our lifetimes and generations before, and it completely breaks it apart. And technology such as silicon carbide and all the design around that electrification is creating new opportunities for devices that haven't existed in the past.
On the demand side, I think I saw a stat that says we're, in the United States alone, we're looking at 4,000 terawatt hours. And by 2050, we're going to need 2,000 terawatt hours just for electric vehicles.
Yeah, it's phenomenal if you think about all the energy stored in oil and gas. You're now having to convert that into a grid, and the grid is historically a very slow-moving entity. It does not grow fast. There's a tremendous amount of bureaucracy. So as you try to build out new infrastructure, you know, also think about not just the EVs, but those EVs are connected to data centers, and they're turning a lot of data. And that data is also, those data centers are also being used for artificial intelligence. And, you know, they say that roughly 80 to 100 terawatt hours annually are being added just from AI.
Oh, I got a stat here that AI compute requirements are doubling every 100 days, according to the World Economic Forum. And that's going to require more power.
Absolutely. If you look at, you know, NVIDIA is kind of the poster child. And if you look at their recent product, I think it's the H100 processor, it is consuming so much power that if they hit their forecast and they sell about 2 to 3 million units in the next couple of years, you're looking at the power that's greater than the Phoenix area, right? And we have very hot summers with a lot of air conditioning here. So the sheer magnitude of what AI is bringing to us in terms of, you know, writing the ultimate card to our favorite podcast brother, or to, you know, fixing that email to do something very challenging, all that requires energy. You know, a simple Google search requires energy. And now that AI is being applied to each and every one over time, it adds up.
So let's get around to some of the terminology we're dealing with. We've got the kilowatt. We've got the megawatt, and then as referenced earlier, we've got the terawatt. What's a terawatt to the average person? That seems just such a strange concept. It's so big.
A terawatt is just something that it's hard to get the average mind around. It is a fantastic way to think of things from a numerical standpoint, but at the end of the day, you know, if you think about 100 terawatts of power, that's the entire power it takes to power Sweden. You think of it like that. So maybe it's hard to visualize 1 terawatt, but if you have 100 of them, you could power Sweden for a year.
We're looking at power generation demand in terms of terawatts moving forward, not just in the United States, but globally. We're gonna have to crank out this much energy, right?
Absolutely. And, you know, with silicon carbide, you're going to really drive that efficiency state, not just in the grid and how you deliver it, but in every point from the grid to where that energy is being consumed, where you see that display on the screen, or you feel that 2-second acceleration up to 60 miles an hour. You have to be as efficient as possible. And silicon carbide gives you those extra percentages, 10, 15% gain over its traditional technologies. Without that, the magnitude that we would have to grow is insane. And if you think about it, if every meal you ate, you took a small bite and put it aside, and everyone in the world did this every time they ate, and you collected it, what size country could you feed? It's pretty massive. So those small gains in efficiency that silicon carbide brings over traditional technologies, and then the new designs that they enable, which are even more efficient, you could effectively feed a country if that helps you feel that magnitude.
So let's talk about the history of silicon carbide. It hasn't been around forever. Is it a fairly new technology?
It's new by comparison to what you're used to in silicon, for sure. If you look at silicon carbide, it was actually first discovered in a meteor, not too far from where we're sitting today, just down the street a couple hours. And silicon carbide isn't naturally occurring. You have to create it.
Right.
And that creation process requires a tremendous amount of energy unto itself. So it's a little bit of a self-fulfilling prophecy there. And so silicon carbide over the last probably 2 decades has really begun to evolve. And over the last 5 years, silicon carbide has really moved into the mainstream. It has gone from a word that very few know to a mainstream discussion in everything that has to do with power delivery, power conversion, power consumption.
So what's it going up against? What was previous to silicon carbide? What was the dominant form of power energy management?
I think the dominant form was really a silicon-based technology. You were seeing a lot of silicon MOSFETs, silicon IGBTs, very good in their time, but as technology has evolved, as new materials such as silicon carbide have come to play, we're able to take higher efficiencies and higher operating temperatures into our new designs. And that has really brought a lot of capabilities out. And it's actually driven a lot of innovation in our industry.
What kind of innovations?
Well, innovations in packaging for sure. You have a tremendous amount of power going through a very, very small chip. And you have to be able to get that power out in the form of heat. And there's been a lot of cool innovations in how we do some of our own module designs here at Microchip. The inability to switch it faster has driven some new designs in the style of module that we create, trying to get all those inductances down so it can switch much faster. And at the end of the day, all you just need to know is that leads to efficiency. That leads to how we make energy change forms without losing it.
Yeah, so that was one interesting thing we could talk about is conversion. You got it from the power plant where it makes it down to the 110 or the 220 volts in your house. And I know that silicon carbide is involved somewhere in that journey. What kind of implications are there from power plant to residential or office space? What happens in between?
Well, from the power plant, you have to increase the voltage and send it down transmission lines, and everyone hates seeing transmission lines. So the natural desire to build transmission lines meets with a lot of protest or disagreement.
NIMBYism.
Yeah, a little bit of that. And no one wants it in their backyard, but at the same time, everyone wants juice in their house when they need it.
Right.
So what happens is, if you're trying to move more power, you have to do certain things. And let's just make it very simple and say, hey, you need more transmission lines. No one wants those. So you have to be able to be more efficient with how you consume the power. So maybe your power consumption at the plug or at your house is increasing, but if you're delivering it more efficiently, you don't have to send so much at the beginning, right? So silicon carbide is now becoming very synonymous with solid state transformers and the ability to design transformers not from large, heavy iron wires being wrapped around into create a standard transformer, but really now solid state, where you're able to use the natural high voltage properties of silicon carbide to be able to switch these high voltages that are found in the grid so that you can do it very efficiently. So as you walk in the morning, and I'm sure you take your cute little fluffy dog, you find these sections of your neighborhood that might have gray boxes or green boxes, right? Yeah. And those are an eyesore. Most people don't like them. So as solid state comes into play, it gives you the ability to shrink that down. You can get efficiency in a smaller footprint and therefore a much higher density of power, and be able to keep that reliability where your expectation is. Because we live, fortunately, in a place where we don't have to worry if the power is going to be on today or tomorrow. We have the luxury to take that for granted.
It's stable. It's just inefficient.
Yeah, it's certainly stable. And I wouldn't say it's inefficient in a bad way. It's just that, the technology going forward is going to help improve and make it so much more efficient that, we have these opportunities to do a tremendous amount of innovation from every aspect, right? Most people focus on the solar. Oh, I need the panel. Or now they're starting to pay attention and focus on the microgrid and, having the battery in your garage where you can store the electricity for when you need it. You see all sorts of off-grid entities beginning to be formed. Just the other day, I was walking to the store, and I could see that the city had put a new camera up, probably for traffic enforcement. And sure enough, it has a panel there, and it's charging a battery, which then runs autonomously. 10 years ago, we'd have to go trench lines, bring power in. Mm-hmm. So as the world is electrifying, we're also innovating to make it a very sustainable way of life.
Okay, so along the lines of what we were talking about with modern conveniences is we don't really buy DVD players and discs anymore. We stream. We don't necessarily buy maps anymore. We get directions. We don't purchase film. We capture images on our devices. And so what we're looking at is part of the electrification of everything is a departure from the handheld items that we used to have. It's going up into the cloud now. That's going to create significant power demand.
Absolutely. Data center power is probably outgrowing the EV power consumption. Everyone's really focused on the EV power because it touches them every moment of the day, and they don't know if they can make it to work because they didn't charge the night before. But when you think of the data centers that are behind all of our streaming services, all of our games, all of our communications, all of the apps we love on our phone, all of the deliveries we have coming to our house, the need for innovation there is huge. And where we see it is in two areas. We see silicon carbide, and again, back to the high voltage properties that silicon carbide brings, it's a natural for that grid to building of the data center, that conversion right there where you're bringing power off the line into the building. We're seeing a lot of efforts there with solid state transformers, connecting at a point higher in the grid, higher voltage in the grid than you normally would, versus what you're used to in a standard residence or commercial strip. And then the second place that we're seeing in data centers is getting the power from now that location through the data center in the most efficient way. So these are basically transmission lines, but inside the facility, mm-hmm. and to the server, and then the conversion from that power level down to something that your server board could use and your AI processor can be able to automatically dispense your paper towels that you needed.
Yeah, and you're talking about a data center that has a significant footprint. Like we're talking, some of these are football fields big, right?
Absolutely. They're football fields big. I mean, 10, 15 years ago, I was touring data centers for when smart energy was first coming on to the scene. And we were looking at energy consumption and how to measure energy was the biggest rage back then. Right. And what we'd find in these data centers was it's all about how much they could cool it. It was all about energy consumption for cooling. Well, nowadays, that is incredibly important. As you can imagine, high power processing puts off a lot of heat. But what we're seeing now is it's the energy consumption of the processor that's dominating the conversation, and the cooling piece is almost become second order. So it's been a complete inversion in the priorities.
Priorities, but not necessarily the amount. It still requires a lot of energy to cool, right?
An insane amount of energy. I mean, if in 2021, I read a stat somewhere that Google, they used about 18.3 terawatt hours. Okay, 18.3 terawatt hours. Ireland, somewhere around 28, 29 terawatt hours a year. So it kind of puts it into perspective. And back then, in 2021, the estimate that I saw was about 10 to 15% was AI usage. Okay, that's changed orders of magnitude since then.
Yeah, data center energy consumption on the order of a country.
Absolutely. Just for one company. There's a handful of others. There's a handful of others, yeah.
Meta, Amazon, yeah, and they all have their own trillion-dollar investments. So we've been talking so far about electric vehicles. We've been talking about microgrids in the house. That kind of leads itself to the evolution of the technology, what it replaces. You mentioned IGBTs. I would imagine that you don't have to use the existing infrastructure. This will eventually cause, I think you mentioned it earlier, it actually causes smaller, more dense batteries. So you're probably looking at shrinking down the footprint of an existing power system.
I wouldn't say smaller, more dense batteries. I think that's going to happen eventually. It's really the power supply.
Right.
Taking the power from the battery and delivering it to what you want it to go do. And as silicon carbide has that higher efficiency, can switch faster, you have much smaller physical supplies that are needed. So for instance, if you think of a large MRI, so all you athletes out there who've damaged your knee and you've had to go in and get the most common MRI reason, you've probably not seen this massive power supply that's hidden somewhere in the hospital to power that MRI. And those are being shrunk drastically with silicon carbide technology. Plus, if you think of like all the factories and all the motors and the conveyor belts and all the equipment and the presses and all the heat that they have to create to manufacture the very goods that we use every day, those power supplies in the drive circuitry for those and all the conversion and the UPSs that are running in case there is a blackout, all of those are being reduced by 10, 20, 30, and in upwards of 55% of the power.
There's the transmission lines, there's the conversion. Is that the power supply, or is it the conversion and then there's a separate?
I think if the average person realized how many times we're converting electricity from when it's created to where it's consumed,
right,
their minds would blow up. It's amazing. You're converting it from its natural production state potentially upward to high voltage, which you can transmit much more effectively down a wire, and you don't have as many losses. And then you've got to slowly start stepping that down from hundreds of kilovolts to what you get into your neighborhood, and then what you get into the transformer in your front yard, and then what's ultimately bringing in 110 or 220 into your house.
Right. And 110 gives you a little tickle, as the electrician likes to say. 220 is very dangerous.
Dana, I think you know that all too well. I'll trust you on it. I feel like you've maybe had some firsthand experiments there. But at the end of the day, a lot of the silicon carbide designs that we work on have some pretty hefty safety protocols. I mean, even our own laboratories where we test the equipment, we have protocols where you can't be in the same room under certain test conditions, lots of thick plexiglass and safety kill switches all over.
So are there any devices that are specific to this technology? Because silicon carbide is the wafer, right?
Absolutely. Silicon carbide is actually the material that is the wafer is made out of.
Right.
And then we do some work to turn that into a power device that you can turn on and off, and that delivers the power to you. And we then take that and we either package a lot of those into a module if you want a lot of power in a very small area,
right,
or we put this into an individual chip that most everyone can recognize, and that particular chip then can go in. So recently we just released a D2 pack 7-lead package. This is a very, very small package. It could probably fit on the size of your thumbnail, yet it can switch the amount of power that you need to charge an EV car, right? If you have 10 of those in parallel, you can charge an EV car in 6 hours or 8 hours.
So suppose one of our listeners has a use case for this technology. Where would they go? Where could we send them?
Oh, that's a good question, Dana. Microchip.com/SIC is an excellent place to find information. We have a lot of good data there with our products. We have a lot of interesting reference designs if people would like to get a head start and have something to be able to leverage. It's been proven. We have a lot of good resources there that people can learn from and understand how to better utilize silicon carbide in their designs and how to convert it from a traditional style to a modern, more efficient, advanced silicon carbide based design.
Do you have any predictions for the future of silicon carbide?
Absolutely. So silicon carbide is right now at the early stage. I mean, I mentioned earlier that it's only in the last 5 years that it's really started to accelerate.
Right.
So we see silicon carbide just continuing to expand into higher voltages, get further up into the grid, into areas that, today aren't viewed as solid state capable or not in a very cost effective way. We definitely see that occurring over time. We do see a lot of new applications that are still being tested in labs and being evaluated that we never thought would even be possible. But by getting this efficiency and energy density that a silicon carbide device can bring to your design, we're seeing those come to fruition over time. So eVTOL, something you talked about earlier, the ability to have a life-size drone that you could ride on your way to school or to work. You don't have to wait on a bus or a subway. Maybe you just take your eVTOL to the airport. Yeah, and much like with aircraft, which is farther out in time, today obviously EVs continue to grow. Every government has goals to reduce our dependence on fossil fuels, on traditional pollution sources, and we believe that these will continue to grow. Maybe today EVs have hit a bit of a hiccup, but every new technology has a bumpy adoption, right? Every new technology does that. So right now it's a very near-term slowdown, but as the technology evolves, as the charging gets faster, and that's the other thing that silicon carbide brings is, with this high power and high energy density, your ability to charge your car much faster is key. And as devices move up, most car batteries are 400 volts, moving to 800 volts. We've seen designs where you can partition your battery from two 400s in series to look like an 800, oversimplifying it, of course, and you can charge in a much higher rate. And that's one of the big challenges. Range anxiety gets cited quite a bit, but at the end of the day, people also don't want to spend an hour or 40 minutes on the side of the road getting a charge. So as silicon carbide is deployed into more and more fast chargers and the systems are architected to take advantage of it, along with the battery technology evolving, we see silicon carbide EV chargers and fast chargers really taking off. And that's something we should probably come back and talk about sometime.
We're eventually going to get to the point where the experience of refueling a vehicle on the internal combustion side is at par or better with an electrical solution.
I would certainly take that as a great aspirational goal, right? I mean, we want to be as close as possible. People in our generation grew up with one way of doing things, and it's a bit of an adjustment. Our children, our grandchildren are going to grow up with EVs, and that's just the norm they're going to know. And for them, a 5-minute, 6-minute, 7-minute charge time to get quite a bit of range will be on par with gas in their minds.
Yeah, like the iPad for a 2-year-old. My kids, and I don't know if you're sharing this experience, but my kids don't know a world before YouTube. They don't know a world before a phone. They don't know a world before an iPad. And so for them, when we describe what I don't think was that long ago, what you're running into is that blank stare of, what do you mean? You had to put something that explodes into your car to get it to run? It's like, well, yeah, we did, because that was the technology of the day. The idea of plugging in your car was relatively new until I was probably well into old by your definition. So I'm thinking about the evolution of these things in terms of as we electrify our fleet of vehicles worldwide, you electrify trucking, you electrify boats, you electrify planes, you're going to get to that point where the generation coming up, what is that disgusting, foul-smelling liquid? It's gasoline.
Well, it's like a phone booth. It's like our kids looking at a phone booth. They're like, Dad, why are you going to a box to talk?
Right.
Just put it in your pocket and pull it out when you need to.
Right. What is that?
What's that thing on the wall for?
Yeah.
Absolutely.
What do you mean you had to memorize a phone number?
Yeah, it's funny because we talked about the electrification of everything. I kind of I look at my three sons as electrification examples because my first one grew up with DVRs, right? They're the first generation of a DVR. The idea of a device had to be powered on, in standby, but then actively ready and recording. And then my next son had the iPhone and got to do charging and understand battery management and understand use versus battery life. And then the third son had the iPad, and they were able to do streaming movies and streaming apps, and all the data center power behind that was just taken for granted. There's no concept of that. So
Yeah, everything on demand.
everything on demand, absolutely.
Final thoughts.
Well, Dana, thanks for having me here. It's really been a fun time to kind of go back through and think about how electrification has really evolved. I know we're so caught up in the day-to-day world. I hope that the listeners out there have really gotten an appreciation for the sheer scale of the challenge that the industry faces. And they've gotten an appreciation of, while there's a lot of new technology and you see EVs everywhere you go, and you see all sorts of devices being charged and PV on roofs, at the end of the day, the effort to really take this to where people don't have to worry about electricity anymore at the next level of consumption. People don't have to worry about where to charge or how long it's going to take to charge their car. People don't have to worry about, is there going to be a rolling blackout, or can I afford my energy bill during this peak time of the season? The fact that governments will be able to stay out of our way and let us innovate and let technology find a way. I look at that as a really positive outcome here. And I think, technology such as silicon carbide it's really excellent to be as part of this, and to be part of this wave of new energy rollout. When I was in university, everyone wanted to go digital. It was all about servers. It was all about internet, .com this. And nowadays, the power person is super popular. We're the new heroes of the engineering world. Well, I like to tell myself that at least.
No, that was great, Clayton. Thank you.
Clayton is a vice president at Microchip Technology. He manages the silicon carbide business unit. He joins us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.
It's electric. What? Vertical takeoff and landing, not electronic. eVTOL is the E stands for electric.
What's the difference?
Accuracy.